Introducing Avatar XPRIZE Team Northeastern. In designing an on-axis motor controller system integrated into the ROS universe, our team is a contributor to Northeastern's efforts in the ANA Avatar XPRIZE Challenge, a $10 million competition challenging teams to create a robotic human avatar that extends and complements human physical capabilities. Extended reality robotics have a myriad of applications, especially given current conditions. Following the COVID-19 pandemic, so many lost their ability to work due to their workplace's new designation as hazardous. Sure, software developers, some engineers, and others could work from home, but if your job required physical presence, you were out of luck. Robotic telepresence and control has the ability to solve so many problems with distance. Consider, for example, a robotic system in ambulances that allows doctors to treat patients before they even reach the hospital. Extending our presence over distance enables us as humans to solve problems quickly in unknown and even potentially hazardous environments.
The ANA Avatar XPRIZE competition provides guidelines defining a broad range of activities as possible testing scenarios. We decided to focus on a single task amongst these scenarios and align our problem statement with achieving that task. A person should be able to interact physically with the avatar, for example, a simple handshake. There was one question our group was left with. In what ways can we provide a system where a person can navigate an environment from afar and successfully interact with that environment? The ultimate goal of our capstone was to supply a reliable control system capable of contributing to this specific task and scaling to future use cases. We started our project with a physical system designed by a previous mechanical capstone team. This included robotic exoskeleton and avatar arm. We accomplished our goal of precise control by designing a motor controller, including a custom PCB and firmware. On top of this, we implemented an RS-485 daisy chaining to create a controller network between different joints on the avatar and exoskeleton.
Hi, I'm Carl Swanson, and I'm the team lead. I led integration between the mechanical, software, and electrical subsystems.
My name is Anya Derrick, and I was the electrical team lead, directing custom PCB design and fabrication.
I'm Spencer Soshin, and I'm on the CE team. I led the RS-485 protocol and the motor controller firmware development.
My name is Peter Albanese, and I led the research effort for visual feedback and user integration while supporting CE design efforts.
I'm Shay Blackinger-Slocum on the EE team, and I lead team organization and logistics while assisting with electrical design.
I'm Peter Downward, and I'm on the EE team. I lead research efforts on component selection and assisted with PCB design deliverables.
I'm going to talk about design constraints the EE team faced when considering our options for motor control. Keeping our test scenario of precise motion in mind, our first priority was enabling the proper level of control between the PC and motors. The controller should be capable of directing movement within 1 degree of accuracy. This meant the motor controller needed to perform sinusoidal control. We also had to satisfy the torque requirements of the existing motors provided by the previous capstone team. This meant a board capable of supporting 48-volt motors. In terms of communication, we wanted flexibility in choosing between RS-485 or CAN, as we were considering both low latency protocols as options. Finally, seamless integration with the previous capstone team's mechanical construction influenced our design path. Our system required an on-axis absolute magnetic encoder to satisfy this. When we say on-axis, we mean an encoder that could be mounted directly to the physical motor joints across from the motor rotor.
The boards pictured represent the two options we had when moving forward with motor control design. We could purchase an off-the-shelf motor controller like this O-Drive that would be capable of the core functionalities needed to satisfy our project. While this option would allow our CEs to get started on firmware immediately, it did not provide the form factor required by the mechanical design and would need additional components. Our second path would expand on the board started by the previous capstone team. The RevB 2-layer PCB did not have a high enough power rating for the 48-volt motors and lacked filtering, which created interference on communication lines. We decided to go down the path of improving this design and developing a new version of the custom PCB that would satisfy all our motor controller needs.
Our total budget came out to $1,700 to $2,000, which is expected for a robotics project of this scope. Due to global part shortages during our build, our PCB budget had to be increased significantly to enable assembly.
Our team made the initial decision to purchase 2 O-Drives so the electrical and software teams could work in parallel. While the EE team designed the PCB, our software team was able to write firmware and additionally leverage the open source firmware from O-Drive for rapid prototyping. As the O-Drives do not come with stock encoders, we developed our own prototype encoder board that connects directly to the O-Drives. However, we immediately noticed irregularities in motor performance due to the long, noisy spilines between the O drives and the on-axis encoder boards. To solve this, we learned to use an LPKF laser cutter at Northeastern to rapidly develop custom shields. These shields allow for twisted pair spilines to interface directly with the O drives, and the CEs could immediately begin development. The final revision of the electrical team's custom PCB has a 48-volt power rating, which we achieved through specific component selection and a 4-layer design. We chose a DRV8301 driver chip as it has an internal buck regulator enabling fewer components down the line. We moved to a 4-layer board to improve not just power and thermal performance, but to optimize signal routing for low latency communication. This board has both RS-485 and CAN capabilities, and we included select pins for smooth transitioning between the two. The signal routing also allows for reliable spilines between the STM32 microcontroller to the encoder on the reverse side. As you can see, when the board is mounted to a joint, the encoder placement perfectly lines up with the motor rotor. Such integration with the mechanical system was not possible without creating a custom board. Finally, the component selection also supports the firmware written by the software team. Our boards will seamlessly integrate with their design, which we will show in the following demonstration.
Inspired by BenCat's Mini Cheetah, we decided to use Mbed OS for our motor controller firmware because it provides high-level abstraction for things like GPIO and reliable drivers for SPI, serial, and other communication interfaces. This allowed us to focus entirely on writing our custom firmware rather than dealing with low-level details. We wrote drivers that successfully interface with our SPI encoder and motor driver to read positions and to command motor signals. Dependency injection was implemented so that both the encoder and the motor driver objects could share the same SPI resource as they were connected to the same SPI lines on the PCB. In the end, our biggest obstacle was calibration. We were unable to move our motors in a predictable manner with the custom board, which is crucial for calibration. Since we were unable to calibrate motors, we could not perform motor control with our boards. Ultimately, we decided to compromise by using our custom PCBs to read exoskeleton joint positions and send these positions over RS-485 to our ROS control node. This node drives a 2-joint gazebo simulation and a 1-joint O-drive controlled robotic arm in the real world. We chose RS-485 over CAN bus because it can handle a faster data write and it was quicker to incorporate into firmware. We read out position values from the microcontrollers to the PC using a ROS node that interfaces with this RS-485 dongle. The dongle is connected to each controller board in a daisy-chained RS-485 network. Our firmware uses a simple request-response scheme. The node sends out requests to the network asking for a specific ID. The microcontrollers read all requests and respond with the position of the motor they're attached to when their ID is requested.
We included safety considerations both in our design and our recommendations to future teams. Using both OSHA and IEEE standards, we developed a safety protocol for our team members when testing the system. The previous mechanical team provided a great foundation for both the EXO and Avatar, with mounts to prevent vibrations, movement, or tipping. During our Capstone, the user always had the main power switch easily accessible, even when wearing the exoskeleton. A teammate never wears the exoskeleton without another person present during testing. For future teams, we have included an operation manual in our report to guarantee proper use. We also recommend future design teams create an emergency stop, also known as a big red button, for when people external to the team are allowed to work with the avatar.
This block diagram explores our software suite connecting to our physical controller boards. Separate ROS nodes for haptic control and controller management are leveraged to close the loop in position-based control. Here we can see a simulation of our robot in the ROS tool suite. We have Gazebo, RViz, and RQT displayed here. We can easily view the joints in our robot, for example, the elbow joints, the main axle, etc., and we can look at the centers of mass, inertias, and other physical and dynamic quantities associated with our robot. ROS control gives us the ability to easily tune our PID for simulation and real-world applications. And we can see in the bottom right our finely tuned PID with the expected and actual joint positions graphed. Our hardware-in-the-loop simulation demonstrates control of a single axis on the Avatar robotic arm. While rotating this gun and motor in a roadkill setup, you can see how it actively mirrors the motion of the single axis, and when we come to contact with our test object, resists motion and applies a proportional torque back on the user. By leveraging ROS and Gazebo, our team is capable of seamlessly switching from the simulation space to real-world robotic applications. This has been integral in developing our control algorithms remotely during the COVID-19 pandemic. Additionally, bugs that may destroy hardware in real life can easily be found and corrected in simulation before it's too late.
Here we have our full exoskeleton system running on our custom PCBs and translating motion to the avatar arm in simulation and the real world. The boards on the exoskeleton are outputting position commands over RS-485, which are buffered on our master computer and broadcast over ROS topics. Both the gazebo simulation and the avatar control nodes subscribe to these topics and map the commands to motion. Our gazebo simulation includes a fully defined URDF, or Universal Robot Description file. The URDF includes transmissions on each movable joint of the robot. These transmissions are in turn controlled by the ROS control package, which enables the motion you see here. This demonstration illustrates our full design pipeline, from interfacing with the user to testing and simulation, and finally, moving the avatar arm to shake a hand. This is the culmination of our team's combined efforts this year. With our group accomplishing mimicked arm motion and a robust communication protocol, we have positioned future groups to explore new aspects of the project. Through the addition of modular end effectors with our simple board network, the system can be customized for a variety of scenarios, meaning it is ready for anything. The addition of a mobility chassis will allow the avatar system to move freely through its environment, unlocking the user from a strictly stationary experience. Lastly, the continued development of force feedback and the addition of visual feedback for the user will provide an unprecedented level of immersion. Through the integration of a virtual reality headset and 3D cameras on the system, the user will have a full view of the world around the avatar system.